Okay, let's continue our discussion of limits. What we saw the last time was limits can fail to exist in three different ways. So we were looking at functions f of x that are piecewise defined. Piecewise defined, meaning that a lot of times these piecewise defined functions have a graph that has a jump in them, some sort of jump at some point that I'm going to call a, all right? And what we found was that if we look at the limit as x approaches a of f of x in this case, this does not exist. Okay, so this was one type of function where the limit of the function as x approached a particular value, in this case a, that limit failed to exist. Then we looked at functions that have vertical asymptotes. So I might have a function that looks something like this. So here's the graph of the function. And let's call this point A. Okay, so this is my x-axis. And so this is the graph of some function that I'll call g of x. And what we have vertical asymptotes. At x equal a, and let's say x equal b, where x equal b happens to be this point here. Okay. Now, what we found was this. In the case of x approaching a, f of x, we found that this limit is what we called plus infinity. Okay, so on both sides of a, if I look at the limit as x approaches a from the left-hand side of f of x, this is equal to plus infinity. And if I look at the limit as x approaches a from the right-hand side, then this limit is also equal to plus infinity. So since these two limits are equal to one another, and they're both equal to infinity, we write in that case that the limit as x approaches a of f of x is equal to plus infinity. Let's look at b. So if I look at the limit as x approaches b from the left-hand side, then what I see is the values of my function g keep decreasing, and they do so. They tend to minus infinity. And so in this case, we have this limit as x approaches b from the left-hand side of g of x. This is equal to minus infinity, whereas the limit as x approaches b from the right-hand side of g of x, this is equal to plus infinity. Okay? So in this case, all I can say about the limit as x goes to b of g of x is that it does not exist. All right? And then we had another case, and this case is really quite exceptional. We're not going to really deal with functions that behave like this, but we did look at the function h of x equal to the sine of 1 over x. And what we found was that the graph of this function starts oscillating wildly as we get closer and closer to 0. So this is going all over the place. It's getting closer and closer to every value between -1 and 1. And we said that in this case, where we have this wild oscillation, if I look at the limit as x goes to, in this particular case, as x goes to 0 from the right-hand side of h of x, this limit does not exist. All right? Now, if I have a function that's a polynomial, so suppose I have a function f of x equal to some polynomial. I'm just going to write polynomial here. Could be examples, could be something like 5x to the fourth minus 3x squared plus 1, or f of x is equal to x squared plus 4, or f of x is equal to 2x plus 1. So these are examples of polynomials. And we know that the graph of a polynomial is a curve that has no jumps. So this would be the graph of a typical polynomial. It has no jumps, and it has no vertical asymptotes. So in this case, if I'm looking at the limit as x approaches a of f of x, where f of x now is a polynomial, this is simply equal to f of a. So as I approach the point x equal a, either from the left-hand side or the right-hand side, the values of f of x approach the value f of a. All right? So here's a whole class of functions whose limits we can evaluate very easily, because the limit as x approaches some value a of a polynomial is just equal to the value of the polynomial at x equal a. The same thing can be said of rational functions, except we have to look at an exception in this case. So let's let r of x be a rational function. And you remember that a rational function is the quotient of two polynomials. Now, what you found when you studied rational functions was that their graphs can have vertical asymptotes. So the graph of a rational function, r of x, can have vertical asymptotes. And what we found was this, that these vertical asymptotes occur precisely at those values of x at which the denominator, the polynomial that makes up the denominator of r of x, vanishes. So if I have r of x, this is a quotient of two polynomials, p of x divided by q of x, and here p of x and q of x are polynomials. If at x equal a, the graph of r of x has a vertical asymptote, then q of a is certainly equal to 0. Okay. All right. So aside from those points at which the polynomial in the denominator vanishes, equals 0, what we can say is the graph of a rational function has no jumps. So the graph of R of x has no jumps. It can have vertical asymptotes. Again, those vertical asymptotes occur at points where the polynomial in the denominator is equal to 0, or where the rational function is not defined. And otherwise, the graph of the rational function, it has no jumps. So what we can say is this: provided Q of A is not equal to 0, the limit as x approaches A of R of x is equal to P of A divided by Q of A. So at all of those points, at all the values of x for which the polynomial in the denominator is not 0, we can easily evaluate the limit as x approaches a value A of R of x just by evaluating the rational function at A. Okay? So if I have the limit as x approaches 2 of 3x squared plus x minus 3, this is just going to equal 3 times 2 squared plus 2 minus 3, and this is equal to 11. Okay? Or if I have the limit as x approaches 1 of 2x squared plus x plus 2 divided into 3x cubed plus 2x squared minus 1. So here I have a rational function. The polynomial that makes up the denominator is certainly not equal to 0 when x is equal to 1. So the value of this limit is just going to be 3 times 1 cubed plus 2 times 1 squared minus 1, all divided by 2 times 1 squared plus 1 plus 2. And so this is equal to 3 plus 2. This is going to be 4 divided by 5. Okay, so these limits are very easy to evaluate. Now, there are some rules governing evaluating limits. So here are a few of them. These are listed on page. So this is on page 306 of the Stewart book. And what I'm going to do is I'm going to work with a few of them and show you demonstrate how these limit laws work. So these are limit laws. And they're the following. Suppose I have two functions, f of x and g of x. These are two functions. And suppose that the limit as x approaches a of f of x is equal to some number L, and the limit as x approaches a of g of x is equal to some number m. Okay? Then I have the following. I have the limit as x approaches a of f of x times g of x. This is equal to L times m. the limit as x approaches a of f of x plus g of x, this is just equal to L plus m. And the limit as x approaches a of f of x divided by g of x, this is equal to L divided by m, provided m is not equal to 0. Okay? And if c is any real number, then the limit as x approaches a of c times f of x, this is just equal to c times L. Okay, so we have 4 limit laws here. And there are 2 others that I want to mention. And they're the following. If n, so I'll call this 5, if n is a positive integer, and I look at the limit as x approaches a of f of x raised to the n power, this is equal to L to the n power. And likewise, if n is a positive integer, then the limit as x approaches a of the nth root of f of x, this is equal to the nth root of L. And here I have to mention, so in order for this to work, if n is even, L has to be positive. Because I can't take, for instance, I can't take the square root of a negative number, okay? So that's why if n is even, in order for this to make sense, L has to be positive. Okay? Well, suppose I have this. I have the function f of x is equal to 2x minus x plus 1, right? And I want to look at the limit as x goes to, let's make it 1, of f of x raised to the 20 power. Well, I don't want to expand f of x to the 20 power and then evaluate that polynomial. What I'm going to do is this. I'm going to look at the limit as x approaches 1 of f of x. This is equal to, well, it's going to be, this is just the limit as x approaches 1 of a polynomial. So this is just going to be the value of the polynomial at x equal 1. And that, in this case, that's going to be 2 minus 1 plus 1. So that's 2. Now, my 5th limit law tells me that this limit here is going to be 2 raised to the 20 power. If I have, say, 2 functions f of x, so this is another example. Call this example 2. This is example 1. If I have f of x is equal to, let's make it 3x squared minus x plus 2, and g of x is equal to, let's make it x to the 4th plus 2x squared plus 1. And I want to look at the limit as x approaches, let's make it -1 of f of x divided by g of x. Well, this is the limit of a rational function. And so we know that if the polynomial that makes up the denominator of that rational function is not equal to 0 at the point where the limit is being taken, which in this case is -1, if that's not 0, then we know the value of this limit is just equal to the value of the rational function at x equal 1. All right? But we can also apply our limit laws to derive this fact, because we know the limit as x approaches -1 of f of x, this is just going to equal f of -1, which is equal to 3 minus -1, that's 4, plus 2, that's going to be 6. And the limit of g of x as x approaches -1, this is going to be 1 plus 2 plus 1, that's 4. So our limit law, in fact, which one is it? It's going to be our first limit law. No, it's going to be, sorry about that. It's going to be our third limit law. Our third limit law tells us that this limit is equal to 6 divided by 4. Okay, and now we can apply this. So this is our third limit law that I'm applying. And we can apply this because we know that the value of the limit in the denominator is not equal to 0. Okay. All right, let's end this lesson here, and then we'll continue talking more about limits in lesson 4.